In today's video, we are going to be taking a look at reactivity. Specifically, we will be talking about different groups on the periodic table and how they react, and also how their reactivity changes as you move down the group. So when we're talking about reactivity, it's important to remember that we have to talk about either how a metal is reacting or a non-metal, because they do different things. Our metals lose electrons when they react, so our most reactive metals would be the ones that are going to lose electrons the easiest. In other words, that would be are things that have lower ionization energy. So the lower the ionization energy for a metal, the more easily it will lose electrons, therefore the more reactive it will be. So high reactivity for our metals is down by francium, so bottom of group 1. With our nonmetals, it's going to be different. When our nonmetals react, they gain electrons. So our most reactive nonmetal would be something that gains electrons the easiest, so whatever has the highest electronegativity. So that is going to be the upper right-hand corner of the periodic table by fluorine. So remember, fluorine has the highest electronegativity, so fluorine is the most reactive nonmetal. Now, it's worth noting that it's the upper right-hand corner of the periodic table where we have our highly reactive nonmetals, but not group 18, because group 18, the noble gases, are unreactive or relatively unreactive. So even though neon is close to fluorine, that does not have a high reactivity. All right, so we've already been talking about our groups. So group 1, group 2, and so on. We are going to be focusing on groups 1 and 2 at the moment. Those are going to be metals. So typical metal characteristics, and they have very high reactivity because they lose their valence electrons easily. So much so that they do not readily exist in the monatomic form. They do not readily exist by themselves. They exist in nature as compounds and must be extracted from compounds in order to get their pure elemental form. Their reactivity does increase as you move down the group. The group 1 elements are going to be more reactive than the group 2 elements. And again, down towards the bottom. So that would make the corner down by francium the most reactive. Now, francium is a highly radioactive element, so we're not going to really see it in reactions or even in compounds, but that would be the proper corner. So the closer something is to francium, especially being a group 1, the more reactive it is. And then again, as we said a slide or two ago, lower ionization energy equals a higher reactivity, because that would correlate with electrons being lost easier. So question number 1, which atom is the most reactive? Now we will notice that all of these are metals. So group 1, closer to the bottom, is going to be more reactive. So magnesium, calcium, both highly reactive, but group 2 is less reactive than group 1. Sodium, potassium are both in group 1. Potassium is lower, so that's going to be more reactive. We also could have looked up their ionization energy, and potassium would have had the lowest which group 15 element has the least metallic character. So basically what we want to do is look at our periodic table, see what in group 15 is the furthest from the metals. So the furthest from the metals would be nitrogen. And nitrogen is not very metallic at all because it's a nonmetal. Number 3, explain why reactivity increases as you move down group 1, because the atoms get larger, so increase in size, and lose their electrons easier because there is less attraction between the nucleus and the valence electrons since they are larger. All right, so again, as we move down the group, the atoms increase in size. So the nucleus is further away from the valence shell. So there's less attraction between the nucleus and the valence shell. Therefore, the electrons are lost easier. And we have evidence of that with a lower ionization energy. Now we are going to switch gears to our nonmetals and talk about group 17, the halogens. We do need to know that name. So you do need to know that group 17 is called the halogens. All right, they are typical nonmetals. So they'll have high electronegativity. Remember, fluorine has the highest. High ionization energy, and also are so reactive that they cannot exist in nature by themselves, so they do not exist in the monatomic form. In fact, they all are part of the diatomics. So remember, diatomics are things that exist naturally as a two-atom molecule. So hydrogen exists as H2, oxygen as O2, and so on. You'll notice that fluorine, chlorine, bromine, and iodine are all listed there. Now, you may notice that AT is also a halogen. AT is incredibly rare and decomposes very quickly because it's unstable and radioactive, and it decomposes so quickly that it can't even be thoroughly studied. But using trends, we could assume that AT would also exist in the diatomic form. So fluorine, chlorine, gases, bromine is liquid, iodine, and AT would be solids. Fluorine is the most reactive nonmetal, so therefore their reactivity will decrease as we move down the group, as we move away from fluorine. And again, for nonmetals, a high electronegativity equals a high reactivity. So for nonmetals, the most reactive is the one that gains electrons the most easily. All right, group 18, the noble gases. That is a very important group. So we definitely need to know that group 18 is called the noble gases. All right, so obviously, as the name implies, they are all gases at STP, and they have a full valence shell, so they are unreactive, and they can exist as monatomic molecules, meaning just by themselves. So they don't bond with anything, they're stable by themselves because they have a full valence shell. Now, they used to be called the inert gases, but they did have to change that name because they have been forced to react under very high temperature and high pressure. The larger noble gases do react a little bit easier, and they do react with fluorine. But again, not spontaneously. They do not. But anyways, once they did react, they had to change their names from inert, because inert meant unreactive, to the noble gases. And they are still, pretty much unreactive because they do not readily react because they are stable, but can be forced to react under extreme conditions. All right, this middle group here is the transition metals. So groups 3 through 12. The transition metals are going to be typical metals. So all of our metals that we think of, like iron, copper, gold, they are in the transition metals, groups 3 through 12. They are much less reactive than group 1 and 2 metals. They are all solids except for mercury. They all have high melting points except for mercury. And they all can form multiple positive oxidation states. So if you take a look at iron on your periodic table, you'll see it's given a +2 or a +3 as a possible oxidation state. And what that means is when it reacts, it can lose either 2 or 3 electrons because they can lose some valence electrons when they react and some inner electrons when they react. So since they can lose a different number of electrons, they end up with the different positive oxidation states. And we'll have to revisit that when we do naming in our next unit. And then they also make colored ions because they are easily excitable. So when a solution has color to it, because most of our solutions are clear, then usually it contains a transition metal. All right, so now we just have some examples. So question number 1 is what we just talked about. So most of our solutions in lab are clear. When they have color to them, assuming we have not added a dye, it's because they contain a transition metal. So you have to see which one of these shows up in groups 3 through 12. Which one of those is a transition metal? And if we look at the periodic table, that would be iron. Number 2, essentially the exact same question, but this time we are given compounds. So you want to look and see which one contains a transition metal. So it doesn't have to be all the elements. You're looking for just one transition metal within the compound. And we see in choice 3, we have copper. Copper is a transition metal because it's in groups 3 through 12. So copper would be our answer. And in fact, copper nitrate is a nice, pretty blue solution. Number 3, which element at STP exists as a monatomic molecule? What that means is it's a single atom by itself. So it's not going to bond to something else. It is stable by itself. So that is going to be a noble gas, group 18. So now we just need to see which one of these is a noble gas, which one of these is in group 18, and that would be neon. Number 4, we do need to memorize what our physical states are at STP. So group 17 is the only group on the periodic table that contains all 3 phases at STP. My 2 lightest ones, fluorine and chlorine, are gases. Bromine is a liquid, and then iodine and AT are solids. So that is my answer. Number 5, which element in period 4, so that's moving across, so period 4 would be potassium through krypton. So if one of these 4 choices was not in period 4, we would eliminate that. Okay, is classified as an active nonmetal, so a reactive nonmetal. So first off, we could get rid of Ga because that is a metal. We can also get rid of Ge because that is a metalloid. We are left with bromine and krypton. They are both nonmetals, but krypton is not reactive because it's a noble gas, so that leaves us with bromine. So number 6, we know our noble gases do not readily react. They have a full valence shell, so they are incredibly stable. However, they have been forced to react with fluorine under extreme conditions, very high temperature and pressure. The one that would react the easiest would be the one who is the biggest. So Kr would be the biggest. It would have the lowest ionization energy out of our 4 choices. So therefore, Its electrons are held less tightly and it will have a slightly easier time making a bond than the other ones would. Helium would be the most difficult too because its valence electrons are so close to the nucleus. Which element in period 3? So we got to make sure we are picking something in period 3. So if our choice is not in period 3, we would eliminate it. Most reactive metal. Okay, so we get rid of chlorine. That's a non-metal, so that would be a horrible choice. Also get rid of sulfur. Also a non-metal, bad choice. 1 and 2 are both metals. Sodium and magnesium are both pretty reactive, but group 1 is more reactive than group 2, so sodium is our answer. Number 8, which element in group 15 has the most metallic character? So you would want to pick group 15 closest to the bottom or closest to the metals. So if we look at these elements, not nitrogen, because that's at the top of the group, and Bi is at the bottom of the group, so that's going to be closest to francium, and it's down at the bottom of the group. All right, so poor hydrogen. Sometimes it's considered to be a member of group 1, sometimes it's not. So hydrogen would not be considered a member of group 1 because it is a nonmetal, and the rest of group 1 is metals, and it's a gas. And the rest of group 1 is also solids. Number 10, the reason why hydrogen would be considered a member of group 1 is because it has 1 valence electron, just like everything else in group 1. So again, sometimes it's considered to be a member of group 1. Often it is not, since it's a non-metal and a gas. Number 11, why is it highly unlikely that sodium would form a +2 charge? So sodium, 2, 8, 1 for its electron configuration. If it wants to get a full valence shell, it will lose an electron to become 2, 8, which would be very stable because that would be a full valence shell. If sodium lost another electron, that would be 2, 7. That would not be stable, and it would require a lot more energy to remove that second electron also. All right, last thing for the units, just really some vocabulary. Allotropes. Allotropes are nonmetals that can exist in 2 or more forms in the same phase. So our most common example is graphite and diamond. So graphite is made out of carbon. Graphite is pencil lead. Diamond is also solely made out of carbon. They are both solids, but diamond and graphite are incredibly different from each other. So they are both solids, they're both composed of carbon only, but that is where their similarities end. They have different structures, as you can see, and because they are bonded differently in a different structure, they will have different physical and chemical properties. Graphite is soft. Diamond is incredibly hard. Graphite is cheap. Diamond is incredibly expensive. So allotropes have different physical and chemical properties because their atoms are arranged differently. Another example is O2 and O3, oxygen gas and ozone, like the ozone layer. They both contain oxygen, they both are gases, but that's where their similarities end. All right, so here's a common question that we see with this idea. So carbon can exist as diamond and graphite. There's also some other forms too. Compared to the molecular structure, so the way that the atoms are arranged and the chemical properties of diamond, graphite has a different structure and different properties. The atoms are arranged differently, which gives it different properties. Think about it this way: you should never be confused as to if you have pencil lead or a diamond. They are going to be very different because they are arranged differently and they have different properties.